afternoon, and welcome to Chem 400 Office Hours. I'd like to say at the outset, I'm getting over a pretty bad head cold. I've already lost my voice several times this week, and so I just want to give you the heads up. I'm not trying to sound like Tom Waits, and I'm not trying to whisper and be sneaky. This is just my reality right now. So, anyways, hopefully my voice will hold together, and whether I'm whispering or talking like Heath Ledger's Joker, I will be able to answer your questions. Anything and everything that you have to throw at me, we'll work through it together. Oh, no worries. Thank you for your empathy. All right, Miriam. Okay. Thank you so much. Thank you so much. So for the lab 7, yeah. I should be able to get it up and running over the weekend. But also just so you know, I'm actually I'm going to I'm gonna move the deadline for eLab 7 to the end of the semester, I think is what I'm doing. I'm also gonna restructure some labs, so we may have some assignments moved to optional or kind of restructured. So anyways, there's some changes and on the way, and I'm gonna be posting all that. I'm currently working on getting all that situation updated. So the eLab 7 should be up this weekend, and also again I'll post to Canvas the due dates and everything with respect to that situation. And I apologize. I was unbearing myself from emails this morning and answered a bunch of questions concerning it, and I apologize for the confusion. But there will be some actual information coming at the very latest by Sunday. Okay, yes, I got one email about eLab 8. Our lab situation apparently is hurting at the moment. So yeah, I will be overhauling and fixing and kind of doing some restructuring over the weekend. So things should be set to sail smoothly starting Monday. Julia, I can absolutely, excuse me, absolutely go over test questions. Um, uh, once, obviously, with the caveat, once the exam is closed, um, I can totally do exam questions. You let me know which problems you want to see, and we'll get into them. Hmm. You know what? That's a great question. Let me take a look at the syllabus. Yep. Exam 3 closed on Monday. So we are in the clear. All right, let's take a look. Oops, sorry. Hang on. All right, okay. So Julia, let's see. Um, chemical reaction absorbs um, 230 kilojoules of energy from its surroundings. Okay, the surroundings do 14 kilojoules of work on the reaction. What is the total energy change? Okay, so we've been told that a chemical reaction absorbs. Well, first, let's identify what we're trying to find. And we're told, well, we're trying to find the total energy change. So the equation for total change in energy is equal to the amount of energy absorbed or released thermally, which is Q, plus the amount of energy absorbed or released through work. All right, now let's look at what we're given. So we're given in this problem that this, let's see, that the reaction absorbs 230 kilojoules, and we're told that the surroundings do 14 kilojoules of work on the system. Right, which is the reaction, on the reaction. All right, and so when we're told that the reaction absorbs 230 kilojoules of energy, this is giving us our value for Q. And if the reaction is absorbing energy, that means that we're dealing with a positive quantity. So Q is positive 230 kilojoules. We have the surroundings doing work on the symptoms, excuse me, I have symptoms of a cold, system, which when the surroundings are doing work on the system, on the reaction, that means energy is being transferred from the surroundings into the system. So again, the system, the chemical reaction is gaining energy through work. So work will be a positive. If the system was doing work on the surroundings, then our work value would be negative. But here it's positive, so this is 14 kilojoules. So now that we know both our energy transferred thermally and energy transferred through work, this is going to be 230 kilojoules plus 14 kilojoules, which if you add these together, it adds to 244. But you have to ask yourself, what should our significant figures be in this scenario? And 230 is precise to the tens place. 14 is precise to the ones place. And we know that whenever we add two numbers, our answer has to have its last significant digit in the same, with the same place value as the least precise number added, which in this case is 230. So we have to round our answer to the not the second decimal place, to the tens place. So our final answer here, after with the appropriate number of sig figs, is going to be so we're going to round to the tens place. 4 rounds down, so our answer should be 240 kilojoules. Okay, so Julia, when we talk about precision, when we talk about precision, in a measuring sense, right? The sense in which we're using it mathematically here. Precision is defined. I need a much bigger eraser. There we go. Precision is defined by the place value of the last significant digit in a number. So, for example, if you were to look at the number 0.037, its last significant digit is right here. So we would say that this number is precise to the third decimal. If you looked at a number 0.12, its last significant digit is in the second decimal place. So for this number, we would say that it is precise to the second decimal, because that is the place value of the last significant digit in the number. And if we were to add these two numbers together, your calculator would tell you that their sum would be equal to 0.157, which is the correct value. But you have to ask yourself, what should my sig figs look like? And when you add two numbers, you have to look at the least precise number. And between these two, 0.037 is more precise because its final significant digit is further to the right, and 0.12 is less precise because its decimal is its final significant digit is further to the left. So this 0.12 is less precise because it's a quantity that was measured at a larger increment, right, to the first decimal place. If this is 0.12 inches, that's a small amount of inches, but 0.037 is even tinier, so that's more precise. This number is bigger and clunkier compared to the other number we're adding, so we would have to round our answer to match the precision of our least precise number. So this would round to 0.16. Okay, awesome. Julia, I'm so glad. Okay, let's see here. We've got two Julias up in the chat right now. Fortunately, the color of your icons are very different, so it stands out to me. Okay, let's see, Julia, do you have any? Julia, in all honesty, I do not know when I'm going to have all the grading done. What I can tell you, because if you're like wondering, okay, what sense, um, what's my standing in the class? In general, the way that letter grades are determined for Chem 400, it's based on your lecture, which has a weight of 70%, and lab has a weight of 30%. So if you can and this is at the end of the semester once everything is turned in and everything is graded. The way that I calculate your letter grades at the end of the semester is you take your lecture average and you multiply it by 0.7, and then you take your lab average and you multiply it by 0.3, and then you take these two numbers and you add them together, and the sum of their sum is equal to your letter grade. Granted, there are lab assignments that are ungraded. There are problems that need to be corrected that had typos in them on a couple of the exams. And so if you're wondering, like, well, that adds some uncertainty, it totally does. I don't know what they'll come out to be yet because I haven't completed the grading. It's something that I'm currently working on, but I have no way of giving you the answer that you want at this moment in time. I know it's coming at a future date. I don't know what that future date is, unfortunately. Yeah. All right, let's take a look. So how much work is required to change the volume of a balloon from 3 liters to 2.8 liters under a constant pressure of 4.08 atmospheres? All right, so we are being asked to find the quantity of work required to fit this parameter, and work is equal to -1 times the constant pressure times our change in volume, and delta V, change in volume, is final volume minus initial volume. So when we look at what we're given, we are given our constant pressure, 4.08 atmospheres. We're given 2 volumes. We're told our initial volume is 3.0 liters, and our final volume is 2.8 liters. All right, so let's go ahead and take a look. You'll notice that we have V1 and V2 right here and here, which means that we can calculate our delta V. We also have our pressure, so we have enough to calculate work. I'm going to go ahead and start with my change in volume. Final 2.8 liters minus initial 3.0 liters. When you punch this into your calculator will tell you that your answer is 0.2. And if you look at your significant digits, 2.8 is precise to the first decimal place, 3.0 is precise to the first decimal place, and our answer is precise to the first decimal place. So we do not need to round. We do not need to add any zeros. Our change in volume, delta V, is equal to 0.2 liters. Now we can calculate our work. Work is equal to negative pressure, which is 4.08 atmospheres, times our change in volume, which is 0.2 liters. So work comes out to be, I could probably do this in my head, but I'm not going to, because I'm tired and I don't trust my brain to handle the numbers. All right. It comes out to be negative 0.816, and our units are atmosphere liters. All right, now one thing you should be aware of is when you look at sig figs, 4.08 has 3, but our delta V has 1 sig fig, so our answer can only have 1 significant digit. I'm going to wait to round to the end of the problem. But I'm putting these lines here to remind myself that I only have 1 significant digit to deal with. Now, we need a unit conversion here because our current units are in liter atmospheres, and my guess is probably that all of the answers were given in joules. So we need to convert our atmosphere liters into joules. And there we go. 1 atmosphere liter is 101.3 joules. So atmosphere liters cancel. And so we have 0.816, that's negative 0.816, times 101.3, work in joules, comes out to be, okay, so let's see, so our value is negative 82.6608. But we can, again, only have 1 significant digit and 2 rounds down. So this would round to negative 80 joules of work would be required to take a 3-liter balloon under constant pressure, 4.08 atmospheres, down to 2.8 liters. Julia, send me a screenshot of the problem from the test, and I will totally fix it. And not only you, but everybody else who pulled this problem out of the problem bank will get full credit on it. But if you could send me an email with yeah, like a screenshot of the problem, that would be super helpful. And I will get on that business. All right, let's see. A sample of argon at 88 degrees Celsius occupies a volume of 420.6 milliliters. If the sample is compressed to 416.9 under constant pressure, what would the temperature of the sample be? All right. So this is a combined gas law problem. And you'll notice that we are given T1, we're given V1, and we're given V2, and we're asked to find T2. So the assumption that we're rolling with is that pressure, and as you pointed out, moles are constant, so that simplifies our expression down to V1 over T1 is equal to V2 over T2. Now we need to solve for that final temperature. So we need to multiply both sides by our final temperature. So we get it out of the denominator there. This gives us T2 V1 over T1 equals V2. Now we need to isolate our final temperature by multiplying both sides by T1 over V1. So that V1 cancels, T1 cancels. So we get T2 is equal to V2 T1 over V1. And now we have enough to solve this problem. There is one thing that remains to be done, though. We need to convert our T1 from degrees Celsius to Kelvin by adding 273.15. So T1 in Kelvin is, and again, I'm not going to do this in my head because I just don't trust my brain today. 88 plus 273.15. Now this comes out to be, my calculator's telling me it's 361.15 Kelvin. As far as sig figs go, 88 is precise to the ones place, so this number is precise to the ones place, which means it has 3 sig figs. I'm going to use the whole number because you wait to round to the end of the problem, but I'm putting these lines here to remind myself that I'm only dealing with 3 sig figs. All right, my final volume is 416.9 milliliters. My initial temperature is 361.15 Kelvin, but again, I only have 3 sig figs in this number. And my final, oh wait, hang on. Oh, I messed up my volumes, I think. No, final volume compressed to 416.9. And it initially occupies 420.6. All right. Milliliters cancel. All right, now let's crunch our numbers. Over. All right, so our my calculator is telling me that the value for our final temperature is 357.972979. The number keeps going, but we don't have to because we can only have 3 sig figs in this number. 9 is going to round up, so our final temperature will be 358 Kelvin. That is our final temperature. So the sig figs for this problem come from this step right here. So when you add 88 degrees Celsius plus 273.15, 88 is precise to the ones place. 2.73 is precise to the second decimal place. So our answer must reflect the precision of 88 degrees. So its last significant digit needs to be in the ones place, which means that if you round 361.15 to the ones place, it would have 3 sig figs. That's why it has 3 sig figs in this step, and that's why it determines the number of sig figs in our final answer. Yeah. So whenever you're doing any sort of mathematical calculation, you always got to apply the rules for sig figs, including unit conversions. It won't always come out to 3 decimal places. So, for example, if we had added 88.00, then our answer would have 5 sig figs because it would have the 2 decimal places plus the other 3. So it's not that whenever you add Celsius and Kelvin, it always comes out to 3. But you do need to apply the rules for sig figs whenever you convert Celsius to Kelvin, if that makes sense. Let me know if it doesn't. Alrighty. This will probably be our last problem of the day because I got to bounce in about 5 minutes. But when 2.00 moles of fuel are burned, it produces 3,448 kilojoules of heat and does 21 kilojoules of work. What are the values for E and H for this reaction? Delta E and delta H, excuse me. So we know that delta E is Q plus W, thermal energy plus work, and delta H is just delta E divided by the number of moles. So first we'll calculate our change in energy. So we're told that the reaction produces 3,448 kilojoules of heat. So first off, this is Q, and this part's critical. It produces. That means that Q, this value, that if energy is produced, that means that energy is released. So Q is negative 3,448 kilojoules. We're told that the reaction does 21 kilojoules of work. Excuse me. Now, if work is done on the reaction is absorbing that work energy. If the reaction does work on something else, that means that the value is also negative. So work here is going to be a negative 21 kilojoules. So delta E is negative 3,448 kilojoules minus 21 kilojoules. When you add these two together, let me see. Where's my calculator? Here it is. Negative 3,448 minus 21 is negative 3,469 kilojoules. You'll notice that both of these numbers have their last significant digit in the ones place, and our answer has its last significant digit in the ones place, so it does not need any rounding. This is our value for delta E. Now our delta H is equal to delta E, negative 3,469 kilojoules, divided by our moles, 2.00 moles. My calculator is telling me that the answer is negative 1734.5. However, we need to round to 3 sig figs because there are 3 sig figs in our denominator and 4 rounds down. So our delta H is negative 1,730 kilojoules per mole. And that is our value for excuse me, for delta H. Dude, you are so totally welcome. Alrighty, and that brings office hours to a conclusion. Thank you everybody for coming. All the great questions. Truly, I'm glad we were able to dig through some of this stuff.